Okay, guys, so we're starting off with transformers. All right, this is from 2019, May, June. So figure one is a diagram of a transformer. Name the parts labeled X, Y, and Z. So, Justin, X, you see that they have an arrow and it says primary coil. So that makes this the what?
You want anything?
No,
You took food already?
yeah,
Justin, you
I'm
should
a mom.
ask your mom to help you.
She not from the room.
Right. So, Justin, what is this coil? What is the name of this?
The
You could call it,
primary wiring,
you could call it the primary coil or the primary winding,
right?
right? So we could answer this in two ways. This is the primary coil or the primary winding. Both are correct. Now, what is this? What is that?
Z,
Hmm?
Z is the core,
It's easy couple. But we could be more specific, right? We could be more specific. What is that core typically made up of?
soft iron.
Right, so that's a soft iron core. For anybody that's looking at this, the reason why we're using a soft iron core is because soft iron typically is ferromagnetic in nature. And the magnetic fields that are going to be generated in the primary coil, we want to maximize its efficiency. We want those magnetic fields to interact with the secondary coil. If you have a ferromagnetic material, what it allows the magnetic flux to be channeled. So if you have this in air, the magnetic flux would probably look like this. But because you have a ferromagnetic material that with a low permeability, it allows the magnetic field of the primary coil to directly reach or more efficiently reach the secondary coil. And it allows for better power transfer, right? So that's some extra information. And Z, well, with Chucks, this answer is supposed to be here, right? Justin, what was Y? What's the answer for Y?
Secondary coil, or the secondary winding.
Correct. Secondary coil.
These questions is from May, June 2019, right?
Yeah.
I remember that from the past papers, you know.
Kirsten, you okay with everything so far?
Yes, sir.
All right, let's move on. So, Kirsten, I'd like you to read this question quickly.
The transformer shown in Figure 1 was tested and the values for the primary voltage and the secondary voltage were obtained. The data is shown in the table 1 below.
Right.
Read the rest. Oh,
I see. Well, I hear that you're not any best of. You're not the best right now, so I'll read it. Um, so on page 7, plot a graph of VS against VP. Justin, VS is E1. What is VS? What does VS stand for?
Um, the secondary voltage,
Well,
right?
what does VP stand for?
Primary voltage.
Correct. So they want us to determine the gradient S of the graph. Justin, from what you learned last class, what were the main equations you needed to remember for a transformer?
Um,
Remind me.
I remember that off the top of my head. Oh, NP over VP equals to NS over VS.
All right, so NP over VP is equal to NS over VS.
Mm-hmm.
That's what you're saying?
Yeah.
All right.
And IP VP equals to ISPS.
Now let me show you something, right? Let me show you something. If you want, there's another thing you could do. So if I were to swap the VP and the NS, it would still mean the same thing. So another way I could write this formula is NP over NS. I could write it as NP over NS, which is equal to VP over VS. And what this is the ratio of turns. This is how you find your ratio of turns. So you could probably take that down as an additional formula, right? So NP over NS is equal to VP over VS. All right, so Justin, you have that?
Yeah.
Okay, cool. So when we find the gradient, remember the gradient is whatever is on the y-axis versus whatever is on the x-axis. So in this question, what are we plotting on the y-axis? They want us to plot a graph of VS against VP. What is going on the y-axis?
The y-axis will be VS.
Yeah, VS is on the y-axis and VP on the x-axis. Now, when we find the gradient of that, remember, gradient is the change in y over the change in x. What is on the y-axis, Justin?
VS.
So when we find gradient, you effectively finding for VS over VP. That's what you're finding for. You're finding for VS over VP. Right? Keep that in mind. You can probably notice the relationship right here. Watch this. VS over VP. That is the opposite of what? If you look over here, what is that the inverse of?
VP over VS.
Right. So what we'll be finding here is 1 over the ratio of turns. That is what we'll be finding for. So 1 over S. So what we're finding is, we're finding for S. S is the gradient. And that would be equal to 1 over the ratio of turns. That is what we're doing. That is what we'll be doing. Right? So Justin, just to reiterate, nth gradient is like y2 minus y1 over x2 minus x1. You recall that?
Yeah.
Okay. So what if you're minusing y2 from y1, you're finding the what and y.
Very good.
When you're subtracting y2 from y1, you're finding the what and y. So that's what C. If you take away, okay, if your parents used to keep track of your height, if they take your height now and minus it from the height when you was 12, they're finding for your what and height.
Change in height.
Right. So when you minus two different values for y, you're finding the change in.
Y.
So that's what gradient is. The change in y over the change in x. Now, in this situation, on the y-axis, we have VS. So it'll be VS over VP. And we note that VS over VP is just the inverse of VP over VS. So what we are finding is 1 over the ratio of turns. Keep that in mind. Let's look back to the notes that we touched that we made last class. Right? I want to explain something. There's something I need to explain. So, Justin, you there?
Yeah.
Okay. Last class, we said that a transformer is something you could use to either raise the voltage or decrease the voltage. But Justin, can you pull power out from your, you know what I want to say? Can you just make up power? If you put in how much power it was in this question, it was 3,000 watts. If I put in 3,000 watts, can I get more than 3,000 watts out?
No.
No. So if I increase the voltage, what will have to happen to the current? If I'm
Then
increasing,
it decrease.
right, vice versa. So we said that, if you have less turns, you're gonna have a lower voltage. If you have more turns, you're gonna have a higher voltage. Look at this example. How much turns we have here?
5.
And how much we calculated here?
Um,
It right in front of you, don't worry. You can look at it.
25. Oh,
25.
I didn't see it.
25. Now, I want to explain something and I want you to take on an additional formula. What's the ratio? So if we do in the ratio of windings, let's see what we'll get. So if we say NS over NP. The number of turns in the secondary over the number of turns in the primary. What will you get? So we find the ratio of turns or the ratio of windings. I want you to look at that. If I say NS over NP, what will I be finding for there? Well, what would the value be? What is NS? What's the number of turns in the secondary?
25.
And what's the number of turns in the primary?
5.
So what's the ratio to the number of turns?
5 to 1.
5 to 1? 5 to 1. Nah, it wouldn't be 5 to 1, it'll be 1 to 5. Because every one
Oh.
turn here is five turns over here. Think about it. Think about that, right? Every one turn over here is going to be equivalent to 5 turns over here. Does that make sense?
Yeah.
And because that's the case, the voltage is going to stack accordingly. What's the voltage in the primary?
200 volts.
What's the voltage in the secondary?
1000.
Take a note of that. I want you to take note of that. What is 200 by 5?
1000.
1,000. So let's come up with a formula there. So if I want to figure out the voltage, if I want to figure out the voltage in the secondary, all I have to do is multiply the ratio of turns, which we know is NS over NP, by the voltage in the primary. You with me so far?
Yeah.
So if I want to figure out the voltage in the secondary, whatever I find as my ratio of turns, I just have to multiply it with my primary voltage. You sure you with me?
Mm-hmm.
Sure.
Run it through. Run it through again.
Okay, look at this for yourself.
Yeah.
If I take 25 and I divide it by 5, what am I going to get?
5.
And we calling that the ratio of?
Yes.
So one turn over here is equal to how much turns over here?
5.
That makes sense, right?
Yeah.
So we're saying the voltage stacks accordingly. If the voltage here is 200, then the voltage here has to be 5 times that amount.
Right.
So 5 by 200 is?
1000.
5 by 200 is? You supposed to know this? What's 5 by
1000.
2? 5 by 2.
10.
Okay, so it's 5 by 200.
1000.
Right. So that's all I want you to realize. I want you to realize that if you want to figure out the secondary voltage, if you want to figure out the secondary voltage, all you have to do is take the number, the ratio of the turns, and multiply by the primary voltage. That's all you have to do. So I just want you to keep that in mind. Maybe you can make a note about it somewhere. So you could say that NS over NP, this is the ratio of turns. So NS over NP is the ratio of turns, and it's also equal to VS over VP. We saw that. Justin, can you see that? If I take 1,000 and I divide it by 200, will I also get 5?
Yeah.
Watch. What's 1,000 divided by 200?
5.
And what's 25 divided by 5?
5.
Right. So the ratio of turns is equal to NS over NP, and it's also equal to VS over VP. Are you sure you understand that?
Yeah.
Okay. And we're seeing, so Justin, we're seeing, once you have the ratio of turns, we can then use that to figure out the voltage in the primary or the voltage in the secondary. Granted, we have one or the other. Yeah. So you understand?
Yeah.
So if my ratio of turns is 5, that means whatever voltage I have here is gonna be how much times here?
5 times.
Right. If I do the ratio of turns and I get a half, what kind of transformer do we have? A step up or a step down?
We get half.
Yeah, so what if, okay, so look at the situation we have right now. Right now, if we say 25 divided by 5, we're gonna get 5. That means That means we raising the primary voltage by 5 times. So that has to be a what kind of transformer?
Step
A
up.
step up. Step up transformers increase the voltage. Now, if I did this calculation, to find the ratio of turns, and I got something that was a fraction, step up or step down?
Step down.
Right, because that means the voltage in the secondary will be a fraction of the voltage in the primary, which means it will be less than the secondary. Make sense?
Yeah.
So keep those things in mind. Right. So Justin, when we do this, we'll be finding 1 over the ratio of turns, because the ratio of turns, we are saying that it is Vs over Vp. That is what we are saying the ratio of turns is, Vs over Vp. You're comparing Justin, you would share with me, right?
Hmm.
Right, so you're comparing the secondary to the primary. If the secondary have more windings, step up or step down?
This secondary have more windings.
Yeah.
Step down.
No, step up.
It.
I say secondary, right?
Oh yeah.
Yeah, so the secondary has more windings. If the secondary has more windings, it's gonna have a greater EMF. So it's gonna have a greater voltage. If
Right.
the secondary has less windings than the primary, what kind of transformer is that?
Step down.
Step down. Okay, cool. So here what? Let's actually do the graph. I want everybody to take a graph paper and let me do this fast.
If I had the pass paper, I could just do it right.
Yeah, do that. Okay, so we're plotting Vs over Vp. So Vs gonna go on the y-axis. Kira, we're doing 2019 May June. If you have access to the past papers, I'd like you to try something. All right, so I want somebody to help and put a scale. Did they give us a scale? No, they didn't give us a scale. Sometimes they do. Kira, I'd like you to help me come up with a scale. So on the y-axis, it's Vs. For anybody that's confused by that, whatever they list first, that's on the y-axis. Whatever they list second, that's on the x-axis. Keep that in mind. So Vs on the y-axis and Vp on the x-axis, right? Kira, help me come up with a scale. So Vp on the x-axis.
We could probably do so like every one block is 0.5.
Let me see
Oh.
how it work. No,
Maybe that's too small.
well, we go see, right? We go see. Let me see.
Okay.
In physics, your graph must take up more than half of the page. Otherwise, you're gonna lose marks. Your scale cannot be a multiple of 3. You can't say every 3 blocks is 1. Reason for that is because if you divide, okay, Kira, where's 1 over 3? Where's 1 over 3 as a decimal?
0.333333333.
Yeah, we don't like that. We don't like to have recurrent digits. So we're not using any scale that is a multiple of 3. Yeah, you could use scales like 5, 4, 2, those kind of things. 10 even. So Kira, you were saying every 1 block is 0.5?
Yeah.
You want an easy way to check if that'll work?
Yeah.
Okay, so we need, what's the maximum value for VP?
8.
8 is the maximum value, and we are using every 1 is 0.5, right?
Yeah.
So how much blocks would we need to fit that criteria? What would you do?
It'll be 8 divided by 0.5 and
Yeah, and that'll be 16. Because you would need 16 halves to make 8. So let's count and see if we have 16. 1,
okay.
2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Will it work?
Yeah.
Yeah, so now you know a shortcut to see if you're doing nonsense or not. You wouldn't waste your time. Because I saw some others waste all the time with the scale. By the time I write the scale, they realize, nah, this wouldn't work. So Kiara, just keep counting for me.
3.5. Oh wait, the blocks I count.
No, just count. We're gonna go next. I test on your hard
Okay,
maths.
4.5,
You real good
5,
at hard maths.
5, 5.5, 6, 6.5, 7, 7.5, 8.
Right. And this will be 0. Now we need to come up with a suitable scale for the y-axis now. So, Kiara, help me. We have 14, 20, 40, 50, 60, 70. So we need to go up. We can't just stop at 70. We probably need to go up to 80. So you
Yeah.
can come up with that scale.
We could probably do.
Hmm.
Could we do like every 2 blocks is 10?
Yeah, that sounds like a good idea. If we doing that, right? If we doing that, and we going. So we say in 2 blocks is 10, right? 2 blocks is 10.
Yeah, that means like 1 block would be 5.
1 block is 5.
Yeah.
And we want to go to 80, right?
Yeah.
So 80 divided by 5 is 16, right?
Yeah.
Let me see if that'll take up more than half the page. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Does it take up more than half the space? I think so. So let's move on.
Yeah.
Right? 10, 20, 30, 40, 50, 60, 70, 80. So right now, Kira, you seeing everything working out?
Yeah.
Okay, awesome. So now we need to plot. So we're saying that the first point is 1.514. If if 2 big blocks is 10, and each one of these blocks is 5. 5 plus 5 is 10. So if this is 10, and we have 10 units, and each unit would represent 1. So that's quite simple. And we already have 1.5 here, so we're going to go 1.5, 14. That's his point over here. Does everybody understand that? Justin, let me know if you would like me to re-explain that. You sure? So the point was 1.5, comma, 14. No, I write 44. So we go 1.5, and then we go 14. Since we're saying 2 big blocks is 10, then 1 big block. Since 1 big block is 5, then we have 10 small blocks all together. And since we're going up to 10, each small block would represent 1. So you just go 4 spaces after 10 to get the 14 that you need. And that's it. Right, let's do the next point. We need to speed through this because we have plenty of work to do tonight. Next one is 326. Tree 26 is right here. The next one is 545. Guys, I just speed running this. I trust that you all catch the flow of it by now. Anybody confused at all? I need to know, guys. Kira, are you confused?
No.
No? This is easy stuff.
Yeah.
Good. And the next one is 545. This graph starting to look like a what? A curve, straight line. What is it? Let me hear. What does it
Probably
look
a
like?
straight line.
Yeah, it is a straight line. All right, the next point is 653. 653. So to get 653, if this is if this is 50, I'll move 3 spaces up to get the 53, right? And it's in line with 6 on the x-axis, so we're good. The next point is 7.567. Okay, 6.5. Right, so I'm at 6.5 here, 6.5 and 67. So this is 65, 66, 67. All right. And the last point is 872. 872. Okay, so that's what we have. Right? Guys, is everybody okay? Justin, are you okay? I'm asking if you're okay. I didn't see you on
Yep.
mute. You okay?
Yeah.
Did your graph look like this so far?
Yeah.
All right. Kira, are all of these points in line with each other? Tell me.
No.
No. The last 2 points, are they very different from the rest of points?
Yeah.
All right. They are quite different. Those could probably be errors. So these points are error points. So what we'll do is we have to start from the origin. We'll place a ruler at the origin and we'll draw a line connecting most of the points. Now I know that people typically do a best fit, but the case is, Justin, I want you to observe something. And all of these points here, like they're in line.
Yeah.
So those are 4 points in line. And these 2 points, look at where they are. They are very far from the typical standard. So those are most likely errors. So where would you use best fit then? You would use best fit if it was a situation like this. See what I mean? See what I mean, Justin? The points are a lot less further from each other. They're kind of similar. So in this
Yeah.
situation, you would use best fit. And what is best fit? Best fit is where you plot the line and the position of the line will kind of be in between or like the mean of all the points, the average. But I'm saying in this situation, since 4 of the points line up perfectly and 2 don't, chances are those are just errors. So we could ignore those. Kira, you understand? Kira, I didn't hear. Let me know if you're okay with that.
Yeah.
All right. All right, so that's the line I'm going to get. As you can see, the line passes through 4 of the points, 4 out of the 2 points, and that says something. All right, so I trust that everybody is okay. Next up, we need to find the gradient. Justin, to find gradient, how much points do we need? What's the minimum amount of points we need?
2.
What's the easiest point to take from this graph? What is the easiest point to take?
E5 and E45.
Now, let me explain something explicitly. When you plot a graph in physics, you cannot use the points that were given. You need to read off points from the graph directly. You can't do that. The easiest point in this graph is what, Kirsten? You didn't even have to zoom up to look to see it. What's the easiest point in this graph? Starts with O. Starts with O. See if you can figure it out. Okay, I'm not hearing Kirsten. Kira, what's the easiest point to pick from this graph? It starts with O. O-R.
You can repeat what you said. It was breaking up for me.
Kirsten, I mean not Kirsten. Kira, what is the easiest point you could read off from this graph? It starts with O.
Oh.
Yeah, O. Oh my God. No, that. What's the easiest point you could take? I don't know how to zoom in. Just by looking at the graph, you could see it.
The point on the origin.
Yeah, the origin. This graph passes through the origin. So that means the point is 0, 0. Who would have thought? So that's the easiest point. 0, 0. Kira, you understand?
Yeah.
Yeah. And when you're reading off a point, typically you would want to use a different kind of marker. So you see how we use a dot and a circle? Probably use an X for the points that you're reading off to differentiate. So this is 0, comma 0. And we need to figure out one more point. And again, this point we're taking, it cannot be from the results. Has to be a point we read off from the graph. So are you guys seeing any nice points? Yeah, let me know if I've seen any good points. Kara, you seen any good points?
Yeah.
What good points is again?
The first one, the
Where's the first one?
wait,
How many coordinates?
no, never mind, not the first one. Wait, put back the line.
All right.
The fourth one. The
What do you mean
coordinates
by
is
that?
what?
What do you mean by that? The fourth one.
Like the line went directly through it.
So what is that point?
That one is just now wait my zoom taskbar thingy not going down so I can see the bottom. But that's the one that is
So you're saying
50
4,
some on the Y and something on the X.
50 something?
Yeah.
Nah, not chief. That's not it.
Yes, and which one you watching?
I'm watching this one.
That one.
Yeah, because you say
I
4.
was watching.
You
I was
say
watching. I
are
said
you
the
so-
fourth one.
the fourth one. Even by the
Yeah.
fourth one, you can't just as a coordinate. We cannot use the points. We cannot use any of these points. Any of these points we can't use. You need to read off points from the graph.
Okay.
So wait, you meant like the fourth one here?
Yeah.
No.
Oh my god, no, Rajiv. Honestly, I just always make a mistake with that because from a physics lab, I remember like when you're calculating gradients, you're not supposed to use like plotted points, right?
You cannot use plotted points.
Yeah,
You're
I
plotting
end
against
up
yourself.
using
You're
like from
plotting
a
against
physics.
yourself.
Yeah, for like my labs, I end up using plotted points for my gradients. So like for those, I had to do over the graphs for them.
And don't make that mistake. Read off a
Yeah,
point.
I just always mix it up. My bad.
I tell you this point, so we can't use that point. We could, but we're not gonna use it because I gave you that point. Read off a point for me.
But that was the perfect point.
It was, but you didn't say the perfect answer.
Um,
So yeah, come on, put something fast.
the okay. So watch. So on the y-axis are 40,
40.
and then go down the line of 40,
We
and then
probably
go.
shouldn't use that because if you notice it not direct, it not exactly reaching over here.
I can't zoom in so fast, close with my eyes.
You're supposed to have this graph in front of you by now. It's supposed to be drawn, you know?
Yes, but still,
Um,
pencil lines are thick.
that's why they recommend getting a mechanical pencil at 0.5.
Well, I don't know. Probably the one below that. Not your perfect point, the one below the perfect point.
Below the perfect points.
Yeah. The 30 or and
Nah, let me look.
okay.
Hmm. How about this? Kara?
Yeah.
Okay,
Yeah.
we will use that one. I think in doing your lesson by now, You cannot use plotted points. Don't do that. What are you doing? Right? Read off that point from then. That point is, what's that point?
Okay. 50.
Wait, whoa, whoa.
Wait, no, my bad. Sorry, I'm sorry.
Wait. What?
I'm sorry, wait.
That's crazy, bro.
Okay. 65.
65.
6.5. Oh my god. Sorry, the lack of sleep gets into me. I pulled out all nighter last night. Sorry, the lack of sleep gets into me.
I understand. I pull out all night and I missed my quiz. I didn't. I missed class last night. I was supposed to teach. Bye.
Yeah, sorry. Because I pulled out all night of the chem labs and then I went to school today and then whatever.
I'll get
Okay.
a blind. I'll get a blind because I also pull out all night. I do not. So I understand how it feels.
Yeah.
Right? So
6.
6.5 then.
Yeah. And 50. 57.
7. Yeah. So the next thing you need to do, Justin, the next thing, you remember how to find gradients?
Yeah.
Okay, what's the formula for gradients? Remember, is it change in y over the change in x?
Y2 minus Y1 over X2 minus X1.
Right. Now you can label your points anyhow you want to. It's up to you. Which one you want to call x1, y1, and which one you want to call x2, y2.
Use the 6.557 as the Y2 minus Y1.
Wait, me y2 minus y1.
I mean, gosh. Wait. Are we X2 minus X1? X2 X. Oh my god.
Wait. What is
X2
that?
Y1.
Wait. What is a point again? A point is made up of a what and a what value?
X and a Y.
Right. So we're saying we're gonna pick one point as the first point. We're gonna call our first point x1, y1. Then we're
Right.
gonna pick a second point. We're gonna call our second point x2, y2. Which one you want to be the second point? Which one is the first point?
The 0, 0.
It don't matter, eh? You can pick any one. So
Right.
we're saying that this one is the first one. So we go call this.
X1 Y1.
Right. And you would call this,
X2 Y2.
right, let's calculate the gradient right here. So y2 is, what's y2? What's the second point for y? What's the second value for y, not point?
57.
57. What is y1?
0.
Y1 is 0. What is x2?
6.5.
X2 is 6.5 minus 0. So we have 57 all over 6.5. What is 57 over 6.5? Should be like 9 or something.
8.76. Well, like around it's a 9.
All right, 8.76.
Yes.
All right, good. So that's the gradient, right? All right, so the working for the gradient has to go on top. All right, so that's the working for the gradient. Justin, Kiara, and Kirsten, before we do anything, let's observe something. Do you all think that this is a primary? Sorry, do you all think that this is a step up or a step down transformer? What do you all think? What do you all think? Look at the voltages. Justin, when the voltage was 1.5 in the primary, what was the voltage in the secondary?
14.
Did it step it up or decrease it?
Step it up.
Right. So what kind of transformer is this?
Step up transformer.
And how much times bigger are we making the voltage? Hint, check your gradient.
But there. Oh, well, 8.76.
Try it. Multiply 1.5 by 8.76 in your calculator. See where you get. You wouldn't get exact 14, but you might get something close.
15.14.
Right? That real close. Try 3. What is 3 by 8.76?
26.28.
Right? So, Justin, by that logic, right? So so in part D, they want us to use the gradient to figure out the number of turns in the secondary coil. Right? Given that the number of turns in the primary coil is 85. That is what they want us to figure out. You with me?
Yeah.
So we have a couple ways we could figure this out. If you want to go from the, according to what I just now show you, this kind of transformer is a what?
Step up.
Is a step up. So if I want to go from the primary voltage to the secondary voltage, we found the gradient. What do you have to multiply the primary by?
Gradient.
Right, the gradient. Because the gradient represents the ratio of turns. So what do you multiply by? What's the gradient?
8.76.
Right. So in this question, the voltage in the primary is, well, let me say secondary. The voltage in the secondary is 8.76 times the voltage in the primary. So I'll show you this a simple method here. Right? This is a common sense method. Carry understanding everything so far? You have the gradient, you know it's a step-up transformer, and you know whatever the primary voltage is, the secondary voltage is like 8.76 times bigger. We understand that, right?
Yeah.
Okay. So if the primary, so they're saying that figure out the number of turns in the secondary coil if the number of turns in the primary coil is 85. That's what they want you to figure out. All right. Justin, let me show you how we're gonna answer this question. Justin, remind me, is there any formulas that you know? For tell me the main formula you know, like with the NP over VS.
And NP over VP goes to NS over VS.
All right. If we rearrange this, we will get NP over NS is equal to VP over VS. I feel like I should know a real complicated method. I will show you this method just now. It's an easier way to do the question. Justin, if you look at the notes here, right? The ratio was 5. Let me ask you a question. If the ratio is 5, what does that mean? If there was 5 turns in the primary and the ratio is 5, what's the number of turns in the secondary?
5 by 5.
Right. If we know that that is the case, and we know it's a step up, and we have the voltage in the, the number of turns in the secondary, and I wanted to find the 5 turns, what would I have to do with 25 to get 5?
5 by 5.
Right. So let's see what's going on in this question. So they gave us the number of turns in the primary. So the number of turns in the primary is actually 85. Now this is a step up. Where will it have more turns? In the primary or the secondary?
Secondary.
Yeah, in the secondary, right? And look at the relationship again. If we're making the voltage 5 times bigger, that means we need to do 5 times more.
turns.
Correct. So if this is a step up, and we know the voltage is increasing by 8.76 times, that means we need to do how much more turns?
8.76 more turns.
By what? Multiply by what?
85.
Correct. So the number of turns in the secondary is 85 by 8.76. I want you to plug that into your calculator.
Seven four four point six.
Say that again.
744.6.
All right. Kira, you understand now?
Yeah.
All right. I want to show you the more scientific method using the formulas, right? Although this is the easiest method. I think this is the easiest method, right, Justin? And this is the easiest method because in a step up, you know that whatever you're multiplying the primary voltage by to get the secondary, that multiplication factor would also be equal to the factor you're gonna multiply the number of turns by. So I made the voltage in the secondary roughly 9 times bigger. So I would have to use roughly nine more turns than the primary. So you go with that, right? You go with this method, right? I want you to tell me the formulas you know for transformers. What are the formulas you know for transform? What are the formulas you know? What were the formulas we looked at?
Me?
Yeah, what were the formulas we looked at?
Um, we NP over VP equals to NS over VS.
Okay, so we looked at NP over VP, and we said that that is equal to NS over VS. Now let me ask that question, Justin, and this is where this is what is going to make this method hard. When we found the gradient, it was y2 minus y1 over x2 minus x1. So what was on the y-axis here? What was on the y-axis?
VS.
Right, so we found VS all over because on the y-axis we have VS. So it's the change in y over the change in x. So what do we have on the x-axis?
VP.
Right. So we had VS over VP. We had VS over VP. Let's look at something. So the formula we just now came up with, right? So Justin, we just now came up with a formula. We said that NS over NP is the ratio of turns, and we understand that if I want to figure out the ratio of turns, I take the secondary and divide it by the primary to see how much times bigger it is. And we
Yeah.
understand that. And then from this question, you realize that the voltage is also linked by that same concept. If this is 25, then this could be 5 and vice versa.
Yeah.
So I want you to take down this formula. It's a very important formula we just now came up with. So I really want you to take this down. So NS over NP is equal to VS over VP. And what this equation tells you, it tells you the ratio of turns. It says that the ratio of turns is equal to the ratio of voltage. So please copy this down. Make sure you have this formula. Please. Right? Now you could get that formula from the other one we learned, which is this thing over here. You could also get it from this formula. It would be a little more confusing, but you can do it. For instance, if I were to cross multiply the NP and the VS alone, I would get VS over VP is equal to NS over NP. And that is also the same formula. That is also the same formula. But I want you to copy this down. You might have a harder time deriving the formula in the exam, but at least you could remember it. So NS over NP is equal to VS over VP. Kira, way to take that down, please. Kira, you have it down?
Just now, almost done.
Yeah, so just copy that down in bold. A formula for transformers, NS over NP is equal to VS over VP. Kira, do you have it down?
Yeah.
Okay. So Kira and Justin and Kirsten, I want you all to pay very close attention to what's going on. If you understand it, if you understand the concept and you forget the formula, you could figure something out in the exam. So, Justin, Kira, and Kirsten. Kira, let me look at what's going on here, right? I'm putting in 200 volts. And how much volts I getting out?
We can repeat the question, sorry.
You wasn't paying attention.
No, mom, we come at to find out if I was in class.
Okay, good. That's good. So, Kira, look at the primary side. The primary is the voltage you're putting in. So we're putting in 200 volts, and how much we're getting out? How much are we getting out?
200?
We mean we're getting 200 out.
And she asked how much volts we get out?
Yes, I said 200 volts is how much volts you're applying to
Mm-hmm.
the transformer as a primary.
Okay.
I kind of worried about you, Kira. Justin, tell she. Justin, tell she how much voltage you're gonna get out.
1,000.
You're gonna get 1,000. A transformer, you put in a voltage, you either get a lower voltage or a higher voltage. That's it. So Kira, we are putting this is the input here. This is the output. That's why it says AC source. You're gonna apply a source over here, and you're gonna get your output. So Kira, what is my input voltage?
200,
What is my output voltage?
1,000,
How much times bigger did it get?
like 5.
5 times bigger. So what I'm seeing is that relationship is also linked to the number of turns. If you have a raise in voltage, that means you had more turns. So look at this Kira. How much did the voltage increase by? A factor of how much?
What do you mean?
A factor of how much? Like what do you have to multiply 200 by to get 1,000?
5.
5. So what I'm saying is that relationship also applies to the number of turns. If you're getting 5 times more voltage, that means you have to put 5 times more turns. Does that make sense?
Yeah.
Okay, you're sure?
Yeah.
You're not saying that very sure. So like what if this was,
Yes, I'm sure.
okay, well, I'm gonna test you then. What if this was 500 volts? What's the number of turns then in the secondary?
Um, it if it's 500, that means it would be like 2. That would be 2 turns, so it would be like N? Cause like, oh wait, no, in secondary.
Secondary.
Sorry. I wanna say 4.
Oh, Justin, does that make sense? She's saying that to use 4 turns in the secondary, and that'll give us more voltage than in primary. You think that makes sense?
Mm.
How much? If you want to get a step up, if you want to get more voltage, less or more turns?
More?
Oh,
More. So, Kira, you can do it. Think. Look at what happened one more time. The voltage is 5 times bigger. Since it's 5 times bigger, it's 5 times more turns. So, if this is 500 volts, figure it out. Justin, you could try too. Kirsten, you could try as well. What will be the number of turns, what will be the new number of turns in the secondary? Hmm.
Wait. So,
Justin, you think you know? Justin, you confused as well.
nah, trying to figure it out.
Look at this question.
Um,
Look at this again, right? Justin, what we notice here?
Is 5 times more than the primary voltage.
You said current voltage.
No, the secondary is 5 times more than the primary voltage.
What does that mean about the number of turns then?
5 times. Oh,
So if this is now 500, figure it out. Justin, you look like you have the answer. Justin, that's not correct. That's nah. That would be way too much. Again, I'm gonna show it one more time, and that's it. So Justin, was the first? I'm gonna erase the 25. What's the first thing we're looking at?
the voltage.
Okay, what about the voltage?
You're looking at the primary voltage and then the secondary voltage. So you're trying to
Right.
figure out how much more it increased by.
Right. Much more is increased by.
5 times more.
Right. So how much more terms we have to put over here?
5 times more than the primary. Oh, okay.
Okay, so now
Right.
I have to get it, otherwise I'm gonna lose my mind. I'm gonna I'm gonna start tweaking. If I have 500 volts over here, how much turns does that mean I have to put over here? Kira, help me now. Ooh.
if I say 25 again, you go tick out.
Yeah, I would. Why are you saying 25? Is there any logic in the answer?
I don't know what I do. Because, like, I feel like, okay, so, like, if 500 volts is 5 turns, right? So, like, one turn would be 100 volts. And, like,
No,
then,
no, that is not how it works. Actually,
Reggie, I don't
wait,
know.
actually, it could be onto something there. It could be onto something. Yeah, yeah, you're onto something. I like how you're thinking. You'll get the answer that way. Continue. In that same logic. Kira, it's going good. I shut it down a little too
Right.
prematurely.
Um, right. So, if it's 500 volts and it has 5 turns, it's like 500 divided by 5. So, like, one turn is 100 volts.
Right?
And, if, wait, so, like, this side, the secondary side same as 1,000?
Yeah.
Okay.
So asking earlier,
So it'd be like 1,000 divided by 100.
yeah. So what's the answer?
10.
Yeah, that's the answer. 10.
Okay.
But you use a different logic, but that's okay. You still figure it out. Justin, I want you to explain why the answer is 10. Because I thought you'd be the man to figure it out first. And I was a little disappointed. Try to explain why the answer is 10.
Well, my weekend was something like 1,000 divided by 500. I get
Wait,
2,
what?
and then
Oh, wait. Yeah, yeah, yeah. I thought it was divided by 5 is 2, right? You're going good,
and then the number of teams was 5.
right?
So I multiply by 2 and I get 10.
Right, that's correct. That's exactly what you're supposed to do.
Oh, well, my weekend from before I get 50 was wrong. But I figured it out.
Let me understand something. I want to let you figure out something, right? If I use 50 turns, try to figure out the voltage. What will be the new voltage? Try to figure out that for me. So if we use 50 turns instead of 25, what the and the voltage is 500. Try to figure out what the voltage will be. Instead of like figure
25,000.
it out. How much?
25,000.
You said 25,000?
Yeah.
Nah, that's not it. You need to ask yourself, how much more turns is that?
5,000 volts.
Yeah, that's the answer. 5,000. I think you understand it now. So basically,
Yeah.
what I'm trying to say is the ratio of turns is equal to the ratio of voltage. That's what I'm trying to say. So 50 divided by 5 is 10, right? That means whatever your secondary voltage is divided by 500 had to be 10. So 5,000 divided by 500 is 10. Kira, you understand that?
Yeah, I think I understand it now.
You sure? You were saying you understanding everything the whole time, so I real scared. I don't know what you understand.
Listen. I just need to think. It's just my brain not working at the moment, okay? But I am thinking as much as it could go.
All right. I have a question, guys. What if instead of 1,000 volts, I change this to, wait, let me just say this is 200 over here, and this is 100 volts over here. In this situation, this is a step up or a step down?
Step down.
A step down. And if it's a step down, do you think it has more turns or less turns?
Less turns.
Has less turns. So we know that the answer here has to be less than 5. Isn't that the case? Yeah. So see if I could figure out. See if I can figure it out. So 200 and 100, what's the relationship there?
2.5.
Is the final answer?
Yeah.
You're correct. Excellent.
Ah,
Let's go. Get my box now. You can't leave me hanging there. Right. Kira, I want you to explain why 2.5 is the answer. Kira, explain why 2.5 is the answer. So we're saying if the input voltage is 200 volts and the output is 100 volts, how much turns would you need? That's what we are saying. Kira, you there?
Yes, and my gear's turning at the moment.
Okay, so Kira, the first thing we're gonna do, look at the voltage in the secondary and compare it to the voltage in the primary. What's the relationship between 100 and 200?
100.
That's not what I mean. Multiplication. What would you have to multiply 100 by to get 200?
2.
Oh, it doesn't. Wait. You'd have to multiply it by 2, right?
Yeah.
But this is a step up or a step down if you're looking at this.
A
Where's the
step
voltage?
down.
A step down. This is a step down. Which means the number of turns has to be less than the secondary. So 100. Wait, you said to get. Wait, Mark said this. What do we have to multiply 200 by to get 100? 200 by
Um,
what is 100? 100 is what of 200?
a half.
A half. So since 200 is 2 times 100, or in other words, since 100 is a half times 200, then the number of turns will be a half times less. So half by 5 is 2.5. So I'll say it
Oh.
again. The secondary is a half the primary, which means you're going to have half the turns. That's it.
Oh. Oh, it's simple. I think I just overthinking it.
Yeah. And that's where we get the formulas from. So now let's apply the formulas. So Justin, I'm going to show you the mathematical approach. But I hope if all you don't remember the formulas, or they could come up with something in the exam and get all the marks. Or they understand how our transformers work now. Right? So Justin, let's do the formula approach. So Justin, we said that the ratio of what is equal to the ratio of what?
ratio of turns is equal to the ratio of voltage.
How would I find the ratio of turns?
Um, NS over NP.
Right? NS is the number of turns in the secondary, and NP is the number of turns in the primary. We comparing them, right? And how would I find the ratio of voltage?
PS over VP.
Yeah, right. So you're with me, right? You're good.
Yeah.
When we find the gradient. Remember, gradient is y2 minus y1, a change in y over the change in x. The change in y over, in this case, and since what we have on the y-axis,
VS.
right? So we're effectively finding the change in VS over the change in VP. Now, what is VS over VP? That is the
Ratio of voltage.
right between the primary and the secondary. You understand
Yeah.
that? And what is
Yeah.
that also equal to?
Ratio of turns.
Right. You'll see where we're going with this. So we are saying, what we are saying that the ratio of turns is equal to the ratio of voltage. That's what we're saying, right? Justin, that's what we're saying, right?
Yeah.
Okay. Yeah, sure. That's what we're saying.
Yeah.
Good. All right. Let's observe what we have. Do we know what VS over VP is?
Oh,
Be careful what we're saying.
wait,
What is VS over VP? That is telling you how much times what? Explain what VS over VP means.
that's the ratio of voltage.
So in the context of this previous question, what is VS over VP? Like if you find VS over VP, what are you doing? If you say 1,000 over 200, what I mean?
Um,
What is 1,000 divided by 200?
5,
What is the significance of 5 here?
5 times more turns.
And 5 times more voltage. Do you
Yeah.
understand that?
Right.
All right. So is there anything we find that tells us how much times bigger the voltage in the secondary is? That's what G.
Gradient.
The gradient. That's what we found. The gradient. You understand?
Mm-hmm.
Right. Found the gradient. And I want you to understand what you're doing. The gradient is a change in the y-axis over a change in the x-axis. What is on the y-axis?
VS.
What is on the x-axis?
GP.
So when you find
Oh,
the gradient, you're finding VS over VP.
right.
So you're finding that ratio. And hence we verified it. When we multiply the 8.76 by the 1.5, and we get
Oh,
close to
okay.
40,
I see what I'm doing now. I know, see what I'm doing.
so you catch everything.
Yeah, yeah.
Nice.
I know how to work it out too.
Right, and this is the mathematical approach. So we know what VS over VP is. What
VS
is
over
VS over
VP
VP?
is the gradient.
That's the gradient, that's S. That's equal to S.
Yeah.
You put that in.
And they give you NP.
Right.
So you're making, wait, wait. Define for N
Find out
and
the secondary
S.
turns. Number of turns in the secondary, that's what we're finding.
Wait, I'm gonna work it out for
No, you can work it out right here. You don't need to work it out on paper. Tell me. This is real easy. Okay, want to write it down. Okay. All right.
you multiply by 85 on both sides.
I do. Because currently
Right.
I have 85th of NS. I want to find NS. So I need to find the full thing. So 8.76 by 85. And we know what that answer is. That is 744.6. And you can write turns. See, understand both methods?
Yeah.
This method is the intuitive approach. What you found was how much times bigger. Basically, that 8.76 is the number you have to multiply by to get anything. If you want to get the secondary voltage and you have the primary, just multiply by 8.76. If you want to get the number of turns, just multiply the primary by 8.76. You understand?
Yeah.
I'll have a question for you. Kiara and Kirsten. Kiara, Kirsten, and Justin. Check this out. What if they gave you, instead of the number of primary, they gave you the number in the secondary? and they said the number in the secondary is 744.6. How would you find the number in the primary? You see what they're going to do.
Divided by the gradient.
Exactly. Because if to go from primary to secondary and multiply, then the other way around you divide. Perfect. Nice, man. Let's thinking tonight. Let's thinking tonight. That's good. That's good. So Justin, read part 2 now. Oh, by the way, I just want to clear up any confusion. I was saying that the gradients will give us 1 over something. Will give us 1 over something. I want to clear up any confusion if anybody looking at this on YouTube and you're kind of confused. I'm gonna explain something. If you were using this formula and it came up with NP over NS is equal to VP over VS, yes, it's correct. It's just the opposite. If you want, you could invert both sides. And if you flip both sides, you'll get the NS over the NP is equal to the VS over the VP, which is the same thing, right? This represents the same thing as this. And in this situation, you have NP over NS. So, and the gradient represents VS over VP. So in this situation, you have NP over NS and you have VP over VS. So what you would have to do is you can either invert both sides or whatever gradient you get, you can put a 1 over it, right? To get the VP over the VS. Because if I flip VS over VP, I'll get VP over VS. But there's no need to go through all that trouble. You could just look at it the intuitive method. I mean the intuitive way, and you'll get the answer. Right? So Justin, we want to figure out the current in the secondary coil. How are we going to do that? Justin, how are we going to find current in the secondary coil?
Using the IPVP equals the ISVS formula.
Yeah, we could use that. Right. So we know that the current in the primary is 1.8. Right. So here what way to do for me, Justin. Here what way to do for me. I want you to pick a voltage.
Maybe.
But the voltage you pick, right? It has to be from the graph. You're not going to tell me any random value. Let me explain what I'm talking about. So over here, you're seeing that you need to put in a value for VP and you need to put in a value for VS. You what now?
Yeah.
We're going to get that from the graph. Enter our graph, and we can get that from the graph. Okay. So when the primary, do we have any points? I'm asking that first. Do we have any points?
Yeah.
Yeah, we can't use 0, 0. But we could use this. Let me ask that question, Justin. That's 6.5. What does that 6.5 represent?
VP.
That represents VP. And what does 57 represent?
Yes.
Right? So, and so you have a value for the primary voltage and the secondary voltage already.
Yeah.
So what we're going to do is we're going to plug that in. So the voltage for the primary, that was 6.5. And that would be equal to IS multiplied by the voltage in the secondary, which was 57, right? Could you confirm? 57?
Yeah.
Right. So we need to make IS a subject of the formula. How will we do that? Let me just check something real quick. Yeah. How will we do that? How will we make IS a subject of the formula? Justin? Try to answer here.
Divide by 57 on both sides.
Yeah, we divide both sides by 57. So we cancel off. So we're going to divide by 57. If anybody confused out there, this is why we divided by 57. So we cancel off and give us IS. Right, so IS will be equal to the 1.8 by 6.5. What is 1.8 by 6.5?
11.7.
Right, so we have 11.7 divided by 57. What's the answer?
0.205. Oh, 0.21.
0.21 ops.
Yeah.
Let me see if that makes sense, right? Let me see if that makes sense. What kind of transformer is this?
Step, wait, step down.
Is that step down?
Yeah. Wait. Oh, no. Oh, yeah, step up, step up.
Right. Why is that step up?
As the voltage from the primary increase,
It increases. And remind me, if the voltage is increasing, what is happening to the current?
decreases.
So where should have more current, the primary or the secondary?
Primary.
Primary should have more current because it have a lesser voltage.
Yeah.
Is that true here? Can we see that in our answer? What is the primary
Yes.
voltage again?
1.8.
And what do we get for the secondary?
0.21.
It makes sense,
Yeah.
right? You fully understand that,
Yeah.
right? And there's another method they could do. Let me explain this. Justin, a way to take 1.8 and divide it by the 8.76. Tell me away again.
Yeah, same answer.
Right. The reason for that is because if I am increasing my voltage by 8.76 times, I'll have to drop my voltage. I mean, I'll have to drop my current by that amount of times as well. You understand? Let me
Yeah.
explain that one more time. What am I doing with my voltage?
Decreasing.
Decreasing.
Oh, no, wait. Voltage increasing, current increasing.
Right. So if the voltage is increasing, it'll increase by 8.76 times.
Right.
But the current will decrease by that amount.
Right.
Make sense?
Yes.
So let me write it down as an alternative method. In case you see it like that. Justin, you're learning today, right? Like everything making sense.
Yeah.
Like nice, nice. So Justin, write the statement for me. So first of all, what kind of transformer is this?
Step up.
What does step up mean? What is increasing?
The voltage.
And what is decreasing?
Current.
Right. Now the voltage is gonna increase by 8.76 times, and the current is gonna decrease by 8.76 times. So since the power on both sides are the same, if the voltage increases, by some factor, then the current decreases by that same factor. So what we could say is, we could say that the secondary current, that would be equal to the primary current divided by the 8.76. And we know that that is the NS over the NP, but we just plug it in, right? 8.76. And that would be equal to IS would be equal to IP. They gave us IP as 1.8. So 1.8 over 8.76. And you get the same answer, roughly 0.21 amps. So, Kiara, I don't think that confuse you. Let me guess, you're not sure where this formula come from.
No, I remember the formula you gave it us last class.
This is the formula for what? When you multiply IP by VP, what you get? What you getting?
And there's the primary coil and the secondary coil. So it's
Okay, but
like
what is this? What is this? What you finding? What are you finding for here when you multiply I by V? What? I by V is what?
current.
I is current. V is voltage. What is I by V? What is the product of current and voltage? Starts with P. P. Justin, if you want, you can tell she.
No, wait, don't tell me. Wait. I want it. Just not wait.
I didn't hear the question. What's the question?
What is IP by VP?
Oh,
Don't say. And I mean, it's the same concept for IS by VS. But basically, what we're asking only is, what is I by V? What is I by V calculate? That is what I'm asking.
Mm,
Come on, Kira. What is I by V? It starts with P.
wait, what?
Starts with P. What is I by V? Starts with P.
Key?
No, P.
P? Um, 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 wait. I could look back in my book.
Yeah.
Okay. So, it's our P
Yeah. Starts with P.
power.
Yes, it's power. Because what we're saying is the okay, you figure it out. What is IPVP? Define it for the power in the what?
Coil? Wait, and you find
That's two things.
it. Wait, wait.
What does P and S stand for?
Primary and secondary.
So we're saying that the what power is equal to what power?
The primary power is equal to the secondary power.
And that's based on what law?
The one with the F.
F. No, you're talking about Faraday's law? No. No. Justin, what law is that? We saying that if you put in X amount of power, you kind of get X amount of power out. You can't just create power from the bottom. Yeah. You gotta, whatever power you put in, the power you're gonna get out. Oh, where's our rule? Or where's our law? Starts with C. C.
C.
Here I can't see a wiggle. It's on press. It's what hunting. The Okay, I will tell you first with the conservation. I think I give it away.
Conservation of energy.
Yeah, because if you're putting in that amount of energy, you have to get that energy out, right? Remember, power is equal to energy over time. If so, power in a sense is energy. So, Kara and Justin, if I put in a certain amount of energy, I have to get the most I can get is that energy I put in. You understand? Kara, you sure you understand that? Like,
Yes. I'm sure.
wait, I'm trying to raise one of mine, bro. Wait, wait. I could do it, you know. I could do it. I can't. I'm smiling too much. I can't do it when I'm smiling. I'm not serious, please. I generally mean, what do you mean by that? And like the dog, just look at you and then just play the Among Us music. You had to know what I'm talking about.
Yes, I know, I know.
All right, let's do the last question and then we're gonna do another question. They didn't intend to take so long with this one, but at least I'll understand. Um, Justin, read part 3.
The power output will P out of the transformer given that the voltage in the secondary coil is Vs equals to 55 volts.
What do you want you to find?
Power out.
Power. How do you find power?
P equals to IV.
Okay. And the way to find and what they give you the voltage in the.
Secondary.
So we go use the voltage in so we go use the current in the.
Secondary.
So where's the current? Wait, where's the current in the secondary?
Um, wait. 0.21.
Right? And where's the voltage in the secondary?
57.
55.
Huh? Oh, shucks.
What is 0.21 by 55? Yeah, so that should be like 10 or 11 or something around there.
11.55.
All right.
So 12.
11.55.
Yeah.
What is the units for power? Again, you don't speak a man, you should be supposed to know.
Watts.
Yeah. Anytime I ask a little what is power, that should just give it away, I think. What is power? What is power? What's what is power? What is it's a funny joke. A nerd would say. Right, Kira, you copy down part 3? Well, actually, I will send this after. I'll make a copy down this after on the free time. We're moving on to another question. There we go. All right. What is the difference between a conductor and an insulator?
Wait, one second.
Question. Distinguish between a conductor and an insulator.
A conductor is block the current flow, and the insulator is help the current flow.
Well, they don't help the current flow, it allows current to pass,
Oh, yeah.
right? So a conductor allows current to flow. An insulator blocks blocks the flow of current. I like the answer you give, man. Simple and straight to the point.
I feel right now I'm a gap 2 in physics, you know.
That's good. You got
I
it.
had to push again for the one.
Yeah.
Them labs and them the labs and I want to push fast.
They wouldn't push them back to the lab. Your teachers only listen to carnival music. That what going on. That is a day. Push back on it. Anyways, I getting carried away. B. Read part B.
You are provided with the following: an iron nail, a plastic spoon, wait, I know this, a graphite rod,
All right,
and a
where's the
piece of
conductor?
rubber.
Let me not delete that. Where's the conductors?
Wait,
You should not delete
rubber.
it. A conductor is rubber? Nah,
Wait,
man.
wait, 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 wait,
Yes.
wait, wait.
You just don't say a
Oh no,
conductor is a rubber.
the iron nail and the graphite rod and the insulator is the plastic spoon and the rubber.
Where could you find a graphite rod? Where you finding that?
Um, Well then,
Yeah, I guess so. But your pencil,
no.
your pencil is just graphite. Where is right is graphite. Now you know. Right? Draw a simple circuit diagram to show how we can distinguish between a conductor and an insulator. I fed up to this question. This question really easy. Let's just do it fast. So in this question, you need to have a, tell me what you need to have, Justin.
The battery,
Tell a battery. What else you need to have?
switch,
You need to have a switch. I mean, the switch is optional.
and this one is have a light too.
Yeah, because if it's a conductor, what happen?
The light.
Yeah.
If it's an insulator, I would not light.
Right? So you put a resistor to protect the bulb or the LED. Actually, yeah, you put a resistor. We're being fancy here. A resistor is a water current. Remind me.
Kind of lower, so
You
like,
don't know what the current is, resist the current.
oh, yeah.
I guess you could say that. I mean, you're not wrong. You're not wrong. But it resists the current. So if we have like 8 amps flowing, the bulb wouldn't fully get the 8 amps. It would. Yeah. Right? And so we have that. We have a bulb. But we need to put our break in the circuit, huh? We need to put our break in the circuit. Let me put the break in the circuit over here. Right. So this is it. Explain what is meant by an electric current. What is an electric current? So, just explain this fast. You have a battery. You have a battery. When the switch is turned on and you place a material between these 2 points, if it's an insulator, it will block the current flow and the bulb will not light. If it's a conductor, it will conduct the current, allowing current to pass through this gap. And once you close the switch, the bulb will light. The resistor is there just to protect the bulb, right? Because a resistor limits current. Right. That's the reason there. Explain what is meant by an electric current. What is an electric current? What is current?
Current is the amount of electrons flowing in a circuit.
That's charge.
Oh,
You're telling me what charge is. Current is just simply electrons. It's the flow of electrons. What's the SI unit of current? What do we measure current in?
ohms,
Yeah, amperes. And the SI unit is A. So amperes, A, right? State the charge carriers in each of the following: a copper wire and a sodium chloride solution, right? So I don't think you're gonna know this one, but if you have, you should know the first one. Anytime you have a metals have what in them? They have what? What allows, if you look at the structure of a metal, how does it conduct current? All metals have what? So that's what M. It's 2 words.
is something with induction in.
No, no.
No,
Induction have nothing to do with this.
starting with M. Magnetic, something.
No, it starts with, here what I say, right? M. Oh yeah, well I guess, yeah, magnetic does have with an M, but that's not what I'm getting at. That don't make sense. A wire is not magnetic by itself. See, a sensible answer. All metals have what in them? That is 2 words I want to hear.
Mutual induction.
Again, it have nothing to do with induction.
Mm.
Anybody doing chemistry here? They should know the answer. What do metals have in them that allow them to conduct electricity?
I think I have an answer, but I don't know if it's correct or wrong.
Tell me,
Might be wrong.
tell me. That's what
The
M.
magnetic field, but I feel that
No,
wrong.
no, no. Nah.
Yeah.
Electrons?
What's electrons?
Valence?
No.
No.
Well,
Free?
from a
Free electrons?
free electrons or mobile electrons,
Okay.
right? The charge carriers in our copper wire is mobile electrons, right? Yeah, see good there. Sodium chloride. Sodium chloride, that one's simple. But for chem students, that'll be real simple. Summer, Kira. What is what is the charge carriers in a sodium chloride solution?
The Na plus and Cl minus ions.
I don't think they gonna bring a question like this. Because if you don't know chemistry, you're screwed. You don't know, you're not gonna figure it out. The most you might figure out is NaCl, because that's a common thing. Everybody know what NaCl means, right? Next one. Justin, read part 3.
An electric current of 2.5 milliamps flows through a point P in a circuit for 2 minutes. Part A. Calculate the total charge passing through the point P in 2 minutes.
So the definition you told me earlier for current, this is what it is. So you told me is the amount of current for time or something. That is charge. You remember the formula for charge? That was the formula where Q is equal to what?
Q equals to IB. No, Q equals to IT.
Yes, that is the thing. Q is the charge, I is the what?
Current.
And T is the?
Time.
Right. What is the SI
Says
unit for current?
um
Right, but we have milliamps. So we need to convert milli to amps. Milli is what? 10 to what power?
6.
No, no. Milli means a small. You wouldn't multiply by a positive power. You go multiply by a negative power.
Mm.
10 to the power negative 3. If you didn't
Wow.
know that, copy it down now. Anytime you see milli means 10 to the power minus 3. And the time, something about the time,
2
right?
minutes. Get it. Change that to second.
So what would do?
The 60 by 2 is 120.
Yeah. Kira, did you know that milli is 10 to the power minus 3? Did you know that?
Yeah.
Okay. I feel like I don't believe it sometimes, because like based on
No, I just remember that from physics. Like, in physics, they had the whole thing with milli, micro,
suffixes and
nano,
suffixes.
pico, thingy, thingy.
Yeah. Yeah, I remember that. Like milli, micro, nano, farad. Not farad. Like milli, nano, pico, go down the line, nano, etc., etc. All right, so anybody get an answer?
0.3.
Let me see if that's correct. So 2.5 by 10 to the power 3 minus 3 multiply by 120. 0.3, that's correct. 0.3 what? What is the unit for charge? I'll give you a hint. Christopher Columbus.
C.
Yeah. And what does C stand for?
Coulombs.
Right. Don't put Christopher Columbus up. Right, B. B. The charge on an electron is negative 1.6 by 10 to the power minus 19. Calculate the number of electrons passing through the point in 2 minutes. Okay. Again, what formula are we going to use?
Q plus IT.
Right. Remember, current is the amount of electrons flowing in a circuit. So Q is equal to IT. What are we trying to find for? So I want you to assess what we have. They gave you, what did they give you?
Give a charge.
They gave you charge. Where's charge? I'm gonna put that in one time.
Q. Well, 1 minus 1.6 by 10 to the power minus 19.
All right, say no more. What is current?
They didn't give you a current.
They didn't give you current because that's what you had to find for.
Yeah.
Current is the amount of electrons passing a point in a circuit. What is time?
120 seconds.
How are we gonna find for current?
Divide by 120 on both sides.
Right. So do that for my fast. I'll tell you what you get. Kira, can current be negative? Kira, fast. Could current be negative?
Yeah, minus 1.3333333.
Oh, you hear me? Hello,
Yeah, I hear
hello.
you.
Hi.
Yeah, could current be negative?
Yes,
Why?
because it depends on like the direction of the current.
Yeah, that's actually it. That's actually it, Current could go in different directions, and because of that, current is a vector quantity, scalar. Yeah, Justin, tell me the answer again.
Minus 1.3 by 10 to the power minus 21.
All right. Cool. Right. Everybody okay? Guys, everybody all right? Is everybody okay? So that's clear, right? Anybody? Is anybody there? I'm waiting. Justin, you're there, right? Justin, you hear me? Justin? So you're pranking me or no? I feel so. Justin, you there?
Yeah, man.
Yeah, hearing you. So are you think that question correct? Part B? I don't trust it. Oh, do you think you're correct? Well, long story short, it actually isn't correct, right? It's incorrect. So they give you the charge on an electron, and it says minus 1.6 by 10 to the power minus 19. Calculate the number of electrons passing the point in 2 minutes. All right. So from a previous question, we know that the charge is 0.3 coulombs. Does anybody remember what 1 coulomb is? Kira, do you remember what 1 coulomb is? Kira?
Hello.
Yeah, Kira, do you remember do you remember how to find the number of electrons given charge?
Um, the number of electrons given charge.
Yeah. So like we have the charge, right? We had the charge is 0.3 coulombs, and that's how much charge you have in 2 minutes. And the same, now the charge on an electron, on one electron, is 1.6 by 10 to the power minus 19 coulombs. So let me make that make sense for you. In 2
Mm-hmm.
minutes, the charge in the circuit is 0.3 coulombs. And the charge for one electron is minus 1.6 by 10 to the power minus 19. See if you can figure it out. So again, if you leave your phone charging for 2 minutes at that rate, your phone will have a charge of 0.3 coulombs. So
Is it like
how much electrons would I have to go into that to make 0.3 coulombs? If one electron is minus 1.6 by 10 to the power minus 19.
um
You do this. Here I'll ask you. I'm asking a different question. If let me talk about in numbers. If you pay your phone in charge for 20 minutes, right? Actually no.
mhm.
Hmm. Watch it. Let me just say you work for 2 minutes and you get paid $60. And I tell you, in 1 minute you just get paid in 1 minute, you just get paid 30. How much you actually that question too easy. Question too easy. Way too easy. Um let me just say the salary is $90. And I tell you, in 1 minute, you just get $10. How much minutes you know how to work for? If you get 90 and in 1 minute you just get $10, how much minutes you know how to work for? Here, you understand?
90.
So you got
It'll,
paid $90 and in 1 minute you
mhm.
just get $10. How much minutes you know how to work for?
9.
9. It's the same concept over here. So you pay for the charge. It reaches 0.3 C. And charge is the amount of electrons passing through the circuit in a second. So after you leave it, it charges 0.3, right? And what does cause charge to build up? The flow of electrons. So we have 0.3 coulombs of charge. So that's a certain amount of electrons. And do we know how much one electron contributes to the charge? How much does one electron contribute to the charge?
Um,
They say it's over there.
um, negative 1.6 multiplied by.
Yeah. So that is how much one electron is. And we say and it reaches 0.3.
Mm-hmm.
So figure it out. if I reach 0.3 and I know that one electron contributes by 1.6 by 10 to the power 9 minus 19, how can I figure out the number of electrons made up the 0.3? Hmm.
Yeah, no. Modify the drop.
Yeah, Justin, I hearing you. Justin, see if you can figure out this question. So
Transist.
when you charge something, you allow current to flow into it for a certain amount of time. So we let current, and remember, current is the flow of electrons. So imagine you leave your phone charging for 2 minutes, then a certain amount of electrons will enter the battery. We say another is 0.3 coulombs. So if you leave it for 2 minutes and reach 0.3, and one electron is 1.6 by 10 to the power minus 19, how would I figure out the number of electrons? So this over here is the total, and this over here is how much one is. How would I figure out the number of electrons? Kira, again, check it out. Let me show you a similar example. If you get $90, and I tell you, you just get paid $10 a minute, how much hours here? How much minutes you have to work?
9 minutes.
Okay, so if 0.3 coulombs build up, and one electron is that, how are you gonna figure out the total amount of electrons?
0.3 multiplied by
Nah. To figure out the 9, did you divide or multiply?
or divide.
Again, I'm gonna show you a similar example. Let me just say you buy, I don't know how much doubles, it come up to $30. And we say any cost for one doubles is 5. How much doubles you buy? Akira,
6.
you buy 6. So it's the same situation over here. This is the total, and this is how much one is. So you just divide, that's it. So the first answer, I showed you all was wrong. I was waiting to see if anybody would have a problem with it. You all didn't have a problem with it, which is sus. So if you want to figure out the number of electrons, all you're going to do is you're going to take the charge and divide it by the charge of one electron. Right? So N would be equal to the 0.3 all over the minus 1.6 by 10 to the power minus 19. What would that be equal to? Or just to make
Minus
it
4.8.
summer,
Minus 4.8 by 10 to the power minus 20.
let me tell you. 0.3 all over 1.6 by 10 to the power minus 19. Nice. Supposed to get a real big number. A big number means a positive power. Supposed to get like 1.875 by 10 to the power 18. Well, negative. Supposed to get negative 1.875 by 10 to the power 18.
Now I get minus 1.8 minus 1.875 by 10 to the power minus 20.
So what we're doing is divider. It's supposed to
Yeah.
be, you need to be careful how you plug in this into the calculator. Watch this. It is 0.3 divided by this whole thing. Since it's a whole thing, you need to put it in brackets. So put 0.3 divided by 1.6 by 10 to the power minus 19. Anybody with a Casio could plug this in directly, but you have a sharp, so you have to do this. The brackets are important. I feel like you're not putting any brackets.
Oh yeah, I get
Right? So what's the answer you got?
minus 1.875 by 10 to the power 18.
Right? I'm gonna put specific instructions. If any of you are looking at this and I have a shop, what are you doing with your life? What you doing with your life? You're making your life harder. What are you doing? So if you have a sharp. This is what you gotta do. You gotta say 0.3 divided by minus 1.6 by 10 to the power minus 19. You see this whole thing, it counts as 1. So you need to put the brackets. Right? You got, and what's the answer you got again?
Minus 1.875 by 10 to the power 18.
Yeah. Now you can't exactly have a negative number or something. So we could just, you see, charge, like, that's the thing, right? We consider any charge of the electron to be negative. But as for one quantity, so you could just divide it and you'll get a number. You could see that the number is positive. It's okay. Right? And that make more sense. Right? So the answer is 1.875 by 10 to the power 18. Justin has a little bit of electrons or plenty electrons.
A little bit.
A little bit. So you telling me you would
Oh,
be
no.
sad. You would be sad if it had 18 zeros behind your dollar.
Oh no, I watching you. Oh, yeah, watching the wrong value. Yeah.
Yeah, you'd be very happy if you had 18 zeros in your bank.
Yeah.
You would know how to work your hey, you know how much is 18 zeros? Like your whole I feel like your you could buy the world with that. You could buy the world with 18 zeros. You know how big 18 zeros is? I'm making a million look like nothing at all. Nothing. Yeah. But anyways, I'll call it a day today. It's already 9:09. Hey, look, 9:09. But anyways, I'll see you all here next class. Those who I have hard maths with, I'll see you guys in the morning. Kira, Kirsten, see you all in the morning. Kira, and I'll be seeing you bright and early.
Of course.
It totally wouldn't be late, right?
Of course not. Who
Right.
am I to be late?
Justin, you could just go on the chat and ask Alia what's going on. She didn't come to this session, so I'm not really sure what's going on. Yeah. All right, so I'll have a blessed night. Be safe. Later, everybody.